Hello, my name is Jefferson Ridgeway, and I was tasked with writing a paper on the principle of mathematical induction, or as mathematicians like to say, mathematical induction, or simply PMI. I was tasked with writing the historical development and accuracy, and also talking about an example and a solution of PMI. I just want to state clearly that I am a computer science major and a math minor, and I have taken discrete mathematics or discrete methods and the foundations of math. And both of those classes we encounter PMI. And just as a student perspective in understanding PMI, I understood it from what my teacher taught me, which I had great professors. I just didn't understand the history behind it, but I'm glad I was able to pick a topic where I could explore the history and the accuracy and understand why the proof is what it is and where it comes from. So it's helped me to appreciate the proof more than just trying to get it right for a homework problem or answer. So the principle of mathematical induction, or PMI, states that if if one, when a statement is true for a natural number n equals k, then it will be also true for its successor n equals k plus 1. And the statement is true for n equals 1, then the statement will be true for every natural number n. So at the time when I learned it, this wasn't it didn't seem that really powerful, but after doing this paper research, it has become powerful and understanding historical development, which I'm about to talk about now. So in the history of it, doing a lot of research on PMI and understanding where it comes from, doesn't really come from much. Meaning that there have been no accounted for certain discoverers of PMI. A lot of people in the Middle East, Asia, Europe, Northeast Africa, people have used PMI throughout the centuries, but there's not been one founder for PMI as it has been for calculus, Isaac Newton. For PMI, we don't have a founder, but we have somebody who was the first recorded person to use PMI directly and explicitly, and that was Blaise Pascal. So Pascal was a mathematician. Well, he was a mathematician towards the later ends of his life, and then after being a mathematician, he became a theologian of sorts. He was born in Clermont-Ferrand in 1629 and died in Paris in 1662. So what was really important about Pascal is the fact that he wrote this proof or this paper called the Treatise of the Arithmetic of Triangles. And this was important for PMI because this is the first recorded time where PMI is being directly and explicitly used. It's not called PMI at the time, but it is being used explicitly and not implicitly. Before Pascal, during this time period, writing the Treatise of the Arithmetic of Triangles, there were not many explicit PMI structures around. People had used it, but it was very implicit. You couldn't really tell how to differentiate the proof from something else that was along in the proof as well. And he found this actually by creating Pascal's triangle and trying to figure out the numbers and arithmetic behind the triangle itself. And like I said earlier, Pascal was not the only one to figure out the PMI as we know it today. Another person to do it, these were two people, two founders. That was Mario Lichess, and who did it in 1562, and Mario Loco, who could have. These are two people who could have potentially founded PMI, but they're not exactly implicit in stating that they did find it. But as I was doing my research, I found out that this proof isn't fully. It has some weak spots. And Michael LeBron said that one needs to know beforehand the formula describing the situation considered, meaning that if no problem is set before and done before using the PMI, it may be hard to conduct a PMI using the proof PMI to get a solution to an answer. So, but to remedy that situation, you can use patterns. And it's also where I learned about how PMI, it can you can use divisibility rules, and you can use different, there's other usages for it, as well as they use RSA encryption. A lot of things that deal with PMI and the logic behind PMI are inputted into and used by the RSA in the encryption algorithms and in the cryptology sector, and just in it's a lot of backbone to a lot of things that we take for granted now. So that's been very interesting to me as well. And again, just as a student of learning this mathematics, it's just been again a joy to see just the process of learning it and learning what it means. And again, like I said, I have two examples I'm going to show you that I was able to pull up from the web, and I'm going to go through them one by one so that you understand clearly and concisely what's going on within the proof. So I hope you enjoy that, and then we'll be back on the other end. Hello, and this is my example of the principle of mathematical induction. Here you see that the question says, prove that 1 plus 2 plus 3 plus n equals n times n plus 1 divided by 2 for any integer n greater than or equal to 1. So here we're going to see the principle of mathematical induction fully at work. So the step one is to basically substitute 1 for every word that you have an n in to make sure that the left-hand side is equal to the right-hand side. So the equation, if n equals 1 on the left-hand side, then on the right-hand side, if you substitute 1 for every word that you see in n, you will have 1 times 1 plus 1, which is 2, divided by 2, which is 1. And since 1 times 1, and since here on step 1, 1 equals 1. Step 2 is true for some k equal to k, n is equal to k greater than equal to 1. That is, everywhere that you see an n, you're going to substitute a k. So in this original equation, we have 1 plus 2 plus 3 plus n equals n times n plus 1 divided by 2. So everywhere that we see an n, we want to put a k. And then step 3 says, prove that this is true for n equals k plus 1. That is, you have the original equation, and then for everywhere that you see a k, it'll be a k plus 1 on the left-hand side, on the right-hand side. Now this is where you will have to substitute your k plus 1 into the equation that you received from step 2. And that is, you're going to have to put k plus 1 divided by 2 here equals k times k plus 1 divided by 2 plus k plus 1. And when you simplify the mathematics, you should receive k plus 1 times k plus 2 divided by 2 equals k plus 1 times k plus 2 divided by 2 on both the left-hand side and the right-hand side. Alright, so here's the second question using the principle of mathematical induction. The second question states, prove that 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 times 2n plus 1 divided by 6 for all positive integers n. So the solution to this is that first step again, like we did in the previous problem, is we first have to show that P1 is true. So on the left-hand side, everywhere that there's an n, we have to substitute a 1 for the n. So 1 squared equals 1. On the right-hand side, we have to substitute in 1 for everywhere that we see an n. So that would be 1 times 1 plus 1, which is 2. And then 2 times 1 plus 1, which is going to be 3. 3 times 2 is 6. 6 divided by 6 is 1. So both on the left-hand side and the right-hand side, 1 equals 1. Step 2 says, we now assume that pk is true and then n equals k. So that means that everywhere that there is an n, there should be a k. So here, that's why you have 1 squared plus 2 squared plus 3 squared plus k squared equals k times k plus 1 times 2k plus 1 divided by 6. Just like in the problem above, it says n squared equals n times n plus 1 times 2n plus 2 plus 1 divided by 6. So step 3, furthermore, is to everywhere that you see a k, you're going to substitute in a k plus 1 on the left-hand side. So we have to show that P of K plus 1 is true by adding K plus 1 squared to both sides of the above statement. So then we'll set the common denominator and factor K plus 1 on the right hand side. And then we'll have this on the left, have this left. So then if we expand K on this side, we'll have the, not almost the same thing, but almost similar. So on the left hand side, you see that we have K plus 1 times K plus 2 times 2K plus 3 divided by 6. So we have started from the statement PK and have shown that 1 squared plus 2 squared plus 3 squared plus K squared plus K plus 1 squared equals the right hand side, which is K plus 1 times K plus 2 times 2K plus 3 divided by 6, which is in fact the P times K plus 1 statement. So again, here was the second problem, and here was the first problem that we discussed, and I just hope that was substantial. Hope that has been helpful to you. All right, so now you have seen me, and I've walked you through some PMI examples, and I just want to dive deeper into Pascal. And yes, I do know, as I stated earlier, that he is not the definite founder, discoverer, father, or inventor of PMI, principle of mathematical induction. However, I do want to just touch on his life because I think his life has brought about many mathematical discoveries and ideas, and he just had a lot of achievements in his life, and being in principle of mathematical induction being one of them. So one of these things that he did, he wrote many theorems, including Pascal's theorem, and that theorem has been taught to myself and has been taught throughout the years and centuries. Another thing is that he was one of the very few people, teenagers to be exact, to make a mechanical calculator in the 16th century, and that's very important. Now we have calculators that we have, and they're so far advanced to something that will come out in the 16th century. But the reason he made the calculator was because his father was having a hard time making tax sense out of his paying his taxes. So in trying to navigate that, he helped his father by making a machine that would help him do his taxes correctly. And I think that's just cool. That he was an inventor of sorts as well, not just a mathematician, but an inventor as well. Also developed Pascal's triangle, which has been taught, and I've learned that as well in understanding, breaking down polynomials, as well as he made. What many people don't really think about is that Pascal was very religious. He made a lot of contributions to Christianity philosophy and theology through his writings. So Pascal was a very distinct, he was very dynamic person. He wasn't just a mathematician, or he wasn't just a theologian, or he wasn't just an inventor or an innovator or researcher, but he was all of those things mixed together. I think that just shows his gifting as a mathematician to have a diverse group of talents and gifts and be able to just use them a variety of ways. Another thing is that he wrote at length for the need of the scientific method, which I think wasn't very important, and that we use today. We use the scientific method today to describe the process of from the hypothesis to the conclusion of what should happen during that time, what should be happening ethically, and as well as just conducting the proper experimentation and what that looks like. So all in all, again, like I stated before, this would be the third time I'm stating this, but Pascal was not, a lot of historians, for a matter of fact, really don't consider Pascal to be the founder or the father of PMI. But in a lot of ways, he laid out explicitly what PMI is. So I think he deserves some credit in that. I also think that Pascal, again, he just had a broad range of talents, and that just showcases that mathematicians are not one-dimensional people. They're not just strictly logical, but they also have a variety or an array of gifts that can benefit the society as a whole. And I just think Pascal really embodied that, even with the PMI. And I remember doing this and conducting this research, being thankful to know why PMI is important, why mathematicians see it as an indispensable tool of sorts, and just really being able to understand where mathematicians come from, the frame of mind or perspective of where Pascal came from as well, and just really just understanding and just gaining that understanding, gaining that knowledge has made me more appreciative again of PMI, not just PMI, but all of the mathematics that I've learned this semester in the history of math course. And I'm just thankful to have taken this course and just almost develop a love of sorts for mathematics and just understanding where it comes from and being appreciative of the work that's been put in by mathematicians that have come centuries before this time period. So again, I'm just thankful, I'm appreciative, and I'm just blessed by the mathematics that were discovered and founded. And I just see us building on what they founded and building us and just understanding more and more about the mathematics and why it's important. And I just really, again, enjoy reading and understanding why PMI existed, how it existed, what does it mean. And I just really enjoy what I did in this research. And again, I just think Pascal was a great guy, and I just really like what I did. I really did like what I did in conducting this research. So again, thank you for spending time with me, and I hope this video has been a help to you of sorts. All right, have a nice day. Again, my name is Jefferson Ridgeway. I'm a computer science major, mathematics minor at Elizabeth City State University. I'm a junior currently, 2016. Just email me if you have any questions.